And okay, before we go on, one announcement is that we have a banquet this evening, so please take that into account when planning for your dinner. Okay, so please take away.
Right. All right. Well, let me first of all thank the organizers for setting up this wonderful summer school and a lot of interesting lectures. It's also a pleasure to be here in Korea, and likewise, it's a pleasure to see so many new faces entering our field and wanting to learn about scattering amplitudes. So the organizers of this summer school invited me to talk about some basic and pedagogical lectures on scattering amplitudes. Then this prompted me to think about what are the things that everyone working on this topic should know about, and moreover, something that can be condensed into 4 hours of lectures. Okay, and I decided that there is such a topic, and that is the topic of divergences. It is something that is notoriously confusing when you first learn about it, and especially the physics of it is confusing. But on the other hand, divergences appear all over the place when you talk about scattering amplitudes. So I decided to tell you more about that. Of course, we're not going to be able to kind of flesh out all possible details. What I wanted to tell you about is more kind of some systems in which the physics of infrared and ultraviolet divergences has been understood. So this is what we're going to do over the next couple of lectures. So in the first 2 lectures today, we're going to talk about the IR, so long distance divergences. And in the next 2 lectures over the next couple of days, we're going to focus on ultraviolet divergences and the theory of renormalization, as well as effective field theory. All right. So before we start, I wanted to start with a couple of basic comments and about conventions and notation. Okay, so first of all, when we talk about scattering amplitudes, we really talk about some experiment that takes in states. There are typically some wave packets that evolve forward in time. They evolve using the S operator or the scattering operator. And then we measure some outcome of the experiment as the outstate, okay, at some time later in the future. And typically what we're interested in is understanding how it behaves as the function of the energies and angles of the objects. So let me emphasize that in a physical experiment, the size really matters. So this is the size between you kind of create the initial state and then you measure it. It's typically, I mean, it's always finite. So let me call it 1/λ. And what I wanted to emphasize first is that there's really 2 ways of thinking about the S matrix. So the first way is what I'm going to call, for the purposes of this brief introduction, the physical S matrix. Physical S matrix is actually what happens in nature, right? So it's supposed to represent exactly what I told you about. We have some wave packets, evolve them, measure probabilities, and so on and so on. Unfortunately, so one of the aspects of it is that it really depends on the scale of the experiment, lambda. Unfortunately, one of the downsides of this way of thinking is that it's incredibly difficult to actually compute what happens in nature. Typically, you would have to do things like that, computations like that on the lattice, and even that is difficult to do in physical signature. So what we usually compute when we talk about the S matrix is what I'm going to call here the idealized S matrix. Idealized S matrix is all what you've learned about in your books on quantum field theory, like Peskin and Schroeder. And the reason why we use it is that it's easier to compute. Especially, it's easier to compute in perturbation theory. Okay, so let me mention some of the idealizations that we make. Well, for example, I mentioned the wave packets, but actually, when you do these computations with Feynman diagrams, we assume that particles are actually point particles. Okay, so that's one. Another one is that to define the idealized S matrix, we typically start with the asymptotic states in the far past, minus infinity, and then evolve them to infinity. So really the size of the experiment is infinite in this approximation, or lambda is 0. Okay, so roughly speaking, the two of them, well, I put some quotation marks in here, but roughly speaking, the kind of standard S matrix is really related to physics by taking some limits. Okay, and then what happens very often is that this limits tends to break down. They tend to not exist. Okay, so this one specifically here is the one that I wanted to emphasize first because it's related to so-called infrared divergences. There's also many other approximations that we make. For example, we pretend that couplings are constant and small, and this approximation also breaks down, and it leads to the so-called ultraviolet divergences that we're going to talk about in the next lectures. Okay, so this is to emphasize that whenever you hear the word divergence, it's really associated with the formalism that breaks down, not with the physics that breaks down. And that's actually what's so exciting about studying them, because it teaches us what are the approximations or some assumptions that we've made about physics that tend to go wrong. Okay? So before going further, what I wanted to do is give you some further notation. So first of all, I'm going to call the momenta of the incoming particles Pi, and then the momenta of the outgoing particles P prime I, or I is some index labeling the particle. And then I'm going to use the so-called all incoming conventions, in which I'm going to call the momentum of the outgoing particle P prime. I'm going to call it minus P. Okay, this has nothing to do with negative energies or crossing or anything like that. It's just a change of variables. The reason why we do this change of variables is that to simplify our life when it comes to conventions. So let me spell out, first of all, some of the conventions that we're going to use throughout these lectures. So first of all, here I talked about the S operator. Typically, what we want to study is, and what's in the title of these lectures, of the summer school, are scattering amplitudes. So I'm going to use the notation m sub n, where n is the number of particles, and m sub n is the connected part of the matrix element of S. And likewise, I already mentioned, I'm going to use the all incoming conventions. So what this means is that all the momenta are going to be called P, and then the energy component, P0, is going to be either positive for the incoming momenta and negative for the outgoing momenta, simply because of this minus sign in here. Okay, and then lastly, this might be a little controversial, but I'm going to use mostly minus signature, plus, minus, 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 because I have to make some choice. Okay, so this is all there is. I should probably mention here, I forgot to write, that one reason to use these all incoming conventions is that momentum conservation can be written simply as the sum of all the P's is equal to 0, and then we don't have to distinguish between in and out explicitly. Okay, so with this preface, let me move on to the finally talking about divergences. And the first question that I wanted to answer is, what are the infrared IR divergences? Is this font visible at the back? Yeah. Okay. Good. Please let me know if it's if I'm writing too small, and please also let me know if you have any questions about anything I say. Okay. So to understand what are the IR divergences, let me move on to an explicit example. Let's say you have some process in which you have a number of particles in and out. Okay, and then on top of that, let's say this particle here at some momentum p. On top of that, I'm going to pretend that there's a new particle that I'm going to attach to this process. This particle is going to have the momentum k. Okay, so that this here, this object has p plus k. Okay, it's very simple. And then what I can do is I can actually compare how this addition of this new massless particle with momentum k, how it influenced my process. Okay, so the way that I can actually decompose it is that I can write it as the same process that I started with. Oops. Okay, this one. And the only difference between this side and this side is this vertex in which is present here, as well as the existence of the additional propagator with the momentum p plus k. Okay, so to go from left side to the right side, I have to multiply with some numerator n that is responsible for the vertex insertion, and the propagator, which is p plus k all squared minus m squared, where m is the mass of the particle here. Okay? Strictly speaking, it's going to become very, very important that I keep a proper track of the factors of I epsilon in what's going to come soon. But for this purpose, let me just forget about it temporarily. Okay, so the reason why I don't have to care about the numerator is that I'm interested in divergences. Divergences can exist when the denominator goes to 0 in this case. Okay, in fact, if you look at it, we see that we have a simple pole at the position when the denominator goes to 0. So let me just expand it. So we have p squared plus k squared plus twice p dot k minus m squared has to be 0, right? Okay, but now I'm studying Ascari amplitude. So what this means is that all the external particles are on shell. So the momentum of this particle p squared just comes to m squared. So that means that this m squared cancels with this m squared. And likewise, this momentum here is the momentum square of the massless particle, so it's actually 0. So what this teaches me is that the m squared cancels out. So this combination is actually twice p dot k has to be equal to 0. Okay, so we find that there's a divergence when this dot product is 0. Okay, so to understand better the physics of it, let me now commit to a given frame. So I'm going to go to the following frame, Lorentz frame, in which the momentum of the massive particle, I'm going to write it as having some energy and some component, spatial component, like this, so that p squared is equal to m squared. Okay, and likewise for the massless particle, I can write it as k mu is going to be some frequency, omega. I'm working in natural units here. And then omega, say cos theta, omega sine theta, 0. Okay, so likewise, because 1 minus cos squared minus sine squared is 0, then this is the massless frame of a massless particle. And now the spatial component, this cosine, is measuring just the angle between the two particles that are being scattered. Okay, so what this tells me is that now I can actually identify physically where the divergence comes from. So the divergence is going to look like, well, the numerator factor. And then here I have twice p dot k. So I just do the little exercise and I dot all the entries in here. Okay, so there's going to be twice. Everything is proportional to omega. And then I have omega dot e, or omega times e, minus the second component, cos. All right. So now if you wanted to study the divergence, this little exercise told us that there's actually the p dot k actually factors into two pieces. Okay, either this can go to 0 or this can go to 0. So this, the omega goes to 0 limit, is called the soft divergence. Okay, soft divergence is simply the fact that all the components of the masses vector go to 0 at the same rate. And likewise, now I can analyze the second factor, and I can ask, when is it that this goes to 0? Okay, so if I look at it, the cos is bounded between -1 and 1. This e is always bigger or equal to the e squared minus m squared square root. So you would find that if the mass is positive, this factor can actually never go to 0. So the only potential divergence happens if mass of the both particles at the same time is 0. In this case, cos can go to 0 or pi, and we get a divergence. So since cos goes to 0 pi, this is when the two particles become collinear, and this is what we call the collinear divergence. Okay, so collinear divergence is only possible in this case when mass of the second particle is 0, and it happens when the two particles become collinear, when the angle goes to 0. Okay, so this is the basic Taylor model for all kinds of divergences that we're going to encounter in this lecture. Basically, everything that we're going to do is going to be built out of some kind of combination of soft and collinear divergences. We'll see that they can nest within each other. So one particle becoming soft can enable another particle being soft, and so on and so on. Okay, so before moving forward, let me also explain a little slogan that people tend to use. Because we're going to use it, so I wanted to make sure everyone is on the same page. There's two types of divergences that people call real and virtual. Okay, so if I draw a Feynman diagram, let's say something like this, something like this, something like this, we can distinguish between the real radiation. So this part here is called real radiation. And the reason why it's real is that it's a particle that in principle we put here as an outstate, so you can measure it, so it's real. And likewise, these kind of propagators inside are called virtual. And virtual meaning they're inside loops. Okay, so that's the only distinction. And then what we're going to study in these lectures is the contributions from both the real divergences, on which we're going to focus at first. And then we're going to move on to studying virtual divergences. And then in the last part, we're going to see how they talk to each other and how they could even potentially cancel. Okay, any questions at this stage? Okay, so what we're going to do is, in fact, study two theories. Well, we're going to focus mostly on scalar QED. And let me also mention some aspects of gravity. Yep. Yeah, so the question was about the frame, right? The frame was just so that we can get some more intuition about the divergences. Ultimately, whether something is soft or collinear is a frame-independent statement. I just phrased it in this way for intuition.
That's not the notation. So will you use the wavy line? Will you use wavy line as the difference one?
Yes, so the question was about the notation. I'm going to use the wavy line for massless particle and the solid line for massive particle. Okay, any other clarifications? Yes?
Here you're considering the particles to be all outgoing or to be also allow incoming?
Yes, so the question was about the all outgoing. So one exercise that you can do is if this was a incoming part, so if this was an outgoing particle, I would put a minus sign here. This is just the minus sign from my conventions over here. That just flips the nature of the particle. Okay, but you can see that whether I put a plus or a minus doesn't actually change the statement here. Yeah, excellent questions. Okay, good. So let me remind you about. Maybe I should clarify why I'm going to focus on these theories. So first of all, I'm going to focus on QED, and the reason why I'm focusing on QED is that the story of infrared divergences is completely understood in the QED case. It is not understood in non-abelian gauge theories all the way. And the reason why I'm going to focus on scalars is that scalar QED essentially teaches you all the physics you need to know about the IR without additional complications with spinors and so on. Okay, and I'm also going to talk on gravity because I just think it's cool. That's the only reason. Okay. So let me remind you about the interactions in scalar QED. So let's say we have two particles with the momentum P1 and P2. Then this vertex in here is going to be equal to minus I, the charge E, and then P1 minus P2 with the leftover index that is eventually being contracted with the polarization vector of the massless particle. Okay, so this thing here is the charge. In fact, sometimes it's confusing, so let me just call it E1, so that this is really the charge of the first particle. Okay, and then likewise, you can also repeat the same story with scalars being coupled to gravitons. Okay, so likewise, I have two scalars with momenta P1 and P2. And then if I look at the vertex, it's going to be equal to minus I kappa. So kappa is going to be the gravitational coupling. And then here I'm going to have some function that depends on it's quadratic in the momenta. So it's P1, P2 plus P2, P1, and then minus eta P1 dot P2 minus m squared. Okay. With the indices mu and nu sprinkled in. Okay, and I guess this is a plus technically.
Sebastian, will you be putting, well, it's not terribly important, but will you be putting arrows on particles and antiparticles?
No, I'm going to work with...
Because for the scalar QED, probably the sign depends on whether it's incoming arrow or outgoing arrow.
Yeah. So the question is about the convention for the particles versus antiparticles. I'm going to pretend all particles are the particles, and then whether I reverse the sign of the charge, that would create an antiparticle. So that's the convention. Okay, very good. So you don't really need to remember all of this, but the reason why these vertices are very important is that they lead to a fundamental result in the theory of infrared divergences, which is called the soft theorems, more precisely Weinberg soft theorems. Okay, so we're going to start with the case of the gauge theory, so scalar QED in this case. Okay, so in the gauge theory, I'm going to consider the following scattering amplitude. I'm going to consider the scattering amplitude with n scalars. So particles 1 through n are scalars, fine. But then in addition to that, kind of mirroring the exercise that we've done in here, I'm going to couple all of this to a single photon. Okay, so in the end, I'm going to consider n+1 scattering amplitude, where the momentum and the polarization of this photon are going to be k and epsilon. And now the question that I wanted to ask is what happens in the soft limit okay, so the soft limit is when the absolute value of the mass's momentum is going to 0. Okay, so this is very simple. It's essentially repeating the same exercise that we've done here. So we're going to study what happens if I have a particle, a scattering amplitude rather, with n particles, and then the extra one, the gamma in here, can attach in all possible ways to any of the other ones. Okay, and then it turns out that the leading divergence comes precisely from, so you see, in principle, this photon could have attached somewhere inside of the loop, somewhere here, somewhere inside of the blob. But it turns out that the leading divergence, the most divergent part, always comes from these attachments to the external legs. The only thing that you have to remember is that this photon doesn't have any preference where to attach. So in principle, you have to sum over all permutations of where it can attach. Okay? So what this tells us well, now it's going to be very easy to write an explicit expression. So we have m, the scattering amplitude with n+1 particles to leading order is going to look like, basically, I'm just going to rewrite this expression in here. Okay. So this expression is, I'm going to have p dot k downstairs. Let me write it, k dot p I. Let me actually, for this purpose, let me not forget the I epsilon factor. And now the only extra thing that you need to remember is that there's going to be a numerator factor. The numerator factor you can just read off from this vertex. So this is what I used to call n. And now it's going to be twice E charge of the ith particle times the epsilon dot pi. Okay, so in principle there's two factors, but by momentum conservation I can write the second one as minus the first one. So that gives me a factor of 2 that I've inserted in here. Okay, and this is not the end of the story. This was just attaching to a single external particle, but what I really have to do is sum over all possibilities. So the final formula is this one. Okay, and as I mentioned, this is really the leading behavior in this limit. That's why I've written it with the factors of plus ... And to leading behavior, to leading order, we see that there's the n+1 particle in the masses limit is diverging, so it goes like 1/k, and then there's some universal factor that multiplies the endpoint amplitude. Okay, so this universal factor here is called the soft factor. All right. So there's actually a very interesting consequence of this soft factor, which is combining the soft limit with the word identity. Okay. So how many of you know what a word identity is in gauge theory? Okay, everyone, okay. So let me write it in this way. Seems like everyone knows it. If I have the particle of the photon, what I can do is I can take the polarization vector of the photon and I can replace it with the momentum of the photon. And the word identity tells me this has to be 0. Okay, it's the statement of the gauge invariance, the amplitude. And now what I can do is I can, instead of writing this, I can apply it here on the right-hand side. Okay, see, the photon does not exist here. The photon only couples for this factor in here. So if I sub in epsilon going to k, is going to be k dot p and k dot p that are going to cancel out. And the only thing I'm going to get left over with is the sum of charges going from 1 to n. So what this means is that if I impose the word identity and I combine it with the soft limit, well, this has to be 0. Generically, Mn cannot be 0. So this actually forces me on the fact that this combination here is 0, which of course you might recognize as the charge conservation. So you see that from this perspective, charge conservation is a natural consequence of studying what happens to gauge invariance in the soft limit. There's a question?
I have a question about the statement of theorem. Two questions. First of all, do I assume that the rest of this Mn is real any divergences, or we don't?
Yeah. Yeah, so the question is about whether we assume that there's no divergences in here, and what we assume, or this actually can be proven, is that in the specific limit as k goes to 0, this is the most divergent piece. So this piece here can have divergences coming from some other internal loops and so on. This is not taking into account here. Here we only study the dependence on k. And the claim is that this is the most divergent piece. Yeah. Yeah. Is the leading? Yeah. The question is in which parameter this is leading. This is leading in the k. Or more specifically, the order parameter that we can use is the absolute value of k. So in principle, there could be corrections, and there will be. These are known as the subleading sub-theorems, in which this whole object here behaves like 1 over k. But there could be also, constant pieces, subleading pieces, and so on and so on. Yeah, so these are known as the subleading sub-theorems. They're actually very interesting. I'm not going to cover them in this lecture, but I'm happy to discuss this afterwards. Okay, so let me move on. Okay, so now we're going to move on to an interesting exercise and repeating all of this in the case of gravity. Okay, so in gravity, we can do the exact exercise, the same exercise. We're going to have n hard particles. So hard is not soft. And then we're going to couple it to a single graviton, G. Graviton has now the degrees of freedom that we have here is the momentum as before, but also we have the polarization vectors. In 4 dimensions, I can write the polarization vector of a graviton as just a product of the epsilons, which are roughly the same as these ones. Okay, so gravitons in 4 dimensions have 2 helicity states, plus and minus. Okay, so then, long story short, if I go through the same exercise, basically everything is the same. The only modification is that you have to, instead of plugging in this vertex for the numerator, you have to plug in this vertex that, roughly speaking, is a square of this one. Okay, and if you do it, the physics is very similar. So you also attach to all possible external momenta. If you work out the numerator factor, it has to be proportional, of course, to the gravitational coupling, kappa. And then all the contractions, this is a little exercise that you can do, are going to amount to dotting the epsilon with the momentum of the particle to which we attach. Well, in a sense, there was nothing else really that could have happened. Okay, and then likewise, we divide by twice kp plus I epsilon. And all of this is the same as before, is to leading order multiplying the Hertz amplitude with n states times this factor. All right, so then what can we do with this? Well, just follow our nose, we follow the previous steps. The next step is going to be applying the word identity. Okay, so here's a slightly more advanced question. How many of you have seen the word identity in the gravity case before? Okay, not as many. So it's another way, name, it's the linearized diffeom invariance. Okay, so let me just give you the answer. We can discuss later on where it comes from. It's basically going to have a very similar statement to the gauge theory word identity. And it's just going to say that I take the epsilon contraction, so the polarization vector of the graviton, and then I'm simply going to replace it by k epsilon plus epsilon k. Mu, 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 mu. Okay? It's a double copy of the gauge theory set. Okay, so I can impose that this is 0. This is the statement of the word identity. Okay, so now it's a cool little exercise to plug in this substitution upstairs. So I'm gonna give you a second to work it out. Okay, if I do it, let me just continue from here. This is going to be equal to, well, this is symmetric, so I can look at one of those factors in here. Okay, so one of the epsilons I'm going to replace with k, so that's going to give me k dot p. This is going to cancel out with the denominator. And then the other substitution is epsilon replaced with itself. So this one is going to stay. So what this means is that I'm going to have k, sorry, for epsilon dot ai, sorry, kappa I, p. Can all of you see it? So the part of the numerator cancelled with the denominator, and the only thing that survives in the numerator is the contraction of the epsilon dot p. Okay. So this is very curious because this constraint, and then this of course is supposed to multiply the mn like this. Okay, so this is a very interesting constraint. Once again, this cannot go to 0, so this forces me for this to be 0. But if the coupling constants were generic couplings, then this would naively try to impose some weird momentum condition on my external momenta. But I know, generically, the only constraint that I get is actually the momentum conservation. Okay, so this tells me I cannot just impose anything else for a generic experiment. That would be weird. Okay, so there's only one way out in which this can be compatible with this. So what's the way out? Yes, exactly. If all of the kappas are the same. So all of the kappas are the same. Is a statement about the universality of gravitational couplings. In fact, this kappa here is typically what we call 8 pi g Newton square root. And the fact that in the soft limit, the compatibility with diffusion invariance forced me on the fact that all the states coupled to gravity in the same way is a perturbative scattering amplitudes avatar of the equivalence principle. Is the equivalence principle because it tells me that all particles have to gravitate in the same way. They have to couple to gravity in the same way. Okay, so now there's a cool exercise you can do. You can go back to your hotel and then try to generalize this. I've explained the case of the spin 1 and spin 2. So there's an obvious question you can ask. I'm just going to give it as an exercise. What happens with higher spin particles? Okay, so a little exercise with understanding how the numerators work for higher spins is going to tell you, or should tell you, that the constraint you're going to get is of this type. You're going to sum over all particles, just like in the case of charge conservation and the equivalence principle. And naively, it's going to tell you that you have to impose the following constraint. Okay, there's going to be this combination of S minus 1, where S is the spin, of momenta that coupled the sums being weighted with the corresponding couplings has to be 0. Okay, and then once again, so of course the special cases of that were S equals 1, in which these factors completely disappear. Then S equals 2 was in which we have only one of those factors in here. So if S is greater than 2, it means that I have to put some weird multilinear constraint on the momenta. And that generically is not possible. And the momentum conservation cannot save us. So once again, there's going to be only one way out of this. And it's going to tell you that the only solution is that all of these couplings have to be 0 if the spin of the particle is greater than 2. There's a question? What happens if S equals to 0? Well, if S equals to 0, then we don't have a word identity in the first place. So it means we don't get a constraint here.
But there's still software, there's still a higher.
Yes, there's still a divergence, yes, in the scalar case. Okay, so what this means is that this is a story that if you study scattering amplitudes, you're going to discover over and over again that the higher spin particles, meaning those with massless higher spin particles rather, meaning those with spin larger than 2, are somehow inconsistent. It's very difficult to make them consistent, at least with the known laws of nature. And in this case, we just found that if you try to couple them to other matter states in the soft limit or the large wavelength limit, there's an inconsistency with it, and it tells you that at least in that limit, all the couplings have to be 0. Yes.
You always consider the anti-symmetry part of the coordination. What about the anti-symmetry extremes?
So the question was about the symmetry. I guess you mean why it's a symmetric tensor? Yeah, you can repeat a similar situation for other antisymmetric options. So it turns out that in 4 dimensions, for example, here, we're not going to get anything because there's only 2 helicity states for the spin spin 2. But in principle, you can repeat this exercise here using a slightly more complicated analysis in the higher spin case, and the conclusion is going to be the same. Yeah, there's a question.
Can you make a similar discussion for the half-integer spin particle?
Yes, that's an excellent question. The question was about half integer. So here I've focused on integer spins, and the answer is yes. I didn't want to get into that because we would have to discuss spinners, but there's a very similar statement, and this, in fact, goes through. So the spin 0, 1/2, 1, 3/2, and 2 are consistent, but anything above that is not for the massless particles.
If you only allow permutations of P, does the same... So I'm thinking about integrable systems.
Yes.
If we have only like permutations of P, does the conclusion that G has to be 0 also apply?
I believe so, but we can look for trouble if we want. Yeah. Okay, excellent. Let me move on since I'm way behind. So now, of course, we want to generalize all of these statements. There's many ways you can generalize them. For example, we already mentioned that you can study the subleading soft theorems. That's a very interesting topic. But what I'm going to do next is instead focus on a different generalization. And it's that of the multiple soft theorems. Okay, so multiple soft theorems, meaning that now what I'm going to consider is I'm going to consider a new process with n particles, which are hard, and then s soft particles. So let me define this as the process. Let's say we stick in QED, in which, as before, I'm going to have a number of hard states, momenta pi, and then on top of that, I'm going to couple soft states. We used to do 1, but now we're going to do s. So what I mean by soft in this case is that all of them are going to have some momentum Ka, and I'm going to take the limit in which the absolute value of all the Kas is smaller than the absolute value of all the Ps. Okay? So let's think a little bit about what are the dominant contributions to these kind of limits. So I'm going to start, yes. Yes.
This sort of divergence has to cancel with the loop.
Yes.
Divergence, so we have to talk about the loop.
This is the question was about why didn't we have to talk about the loops? Because the prediction is that there's going to be some cancellations. And this is actually what I'm going to talk about next. We're going to see that these kind of divergences, if you treat them inside of cross sections and so on, they can actually cancel out. Okay, so this is a great comment. But actually, before trying to understand that, we need to be able to understand the multiple soft theorems. So this is where I'm going to go next. So let me go to the example. In a sense, we've already learned everything there's to know about s equals 1. So the next case is going to be s equals 2. Okay, S equals 2, meaning that let me start drawing similar pictures. We're going to have some process. And then I'm going to try to understand where these soft particles can attach, once again, to leading order. Okay, so the simplest case is that I have two soft particles, and they can attach to some leg I and some leg J. Okay, what else can happen? These are distinguishable, so they can also attach in the opposite order, so like J and then I, like this. Okay, and what else? They can, of course, attach to the same leg, I and I, in succession. And then the last option is that they can attach to the same leg in succession, but twisted in the same way as between here and here. Okay, so hopefully you can see that. Okay, and as before, for now, we're only studying the case of the leading divergences. So these are the leading contributions. Okay, so what we want to do is actually write down a formula similar to the formula that we've seen for the single particle Weinberg soft theorem. Okay, so the formula, let me call these contributions Ij, and these contributions Ii, because these attach to two different particles and these ones to two same particles. Okay, so the contribution from Ij is going to be the same as before. Okay, I'm just simply going to multiply the two soft factors because these two particles don't affect each other. But there's going to be also a new contribution that we'll have to analyze slightly more carefully that is going to come from these diagrams. Okay, so let me write when I say as before, what this means. Is that I'm going to sum over all the ij's with the condition that I is not equal to j. Okay, and then I'm going to get the soft factor epsilon dot pi k dot pi. Okay, and strictly speaking, this is epsilon 1 and k1. And there's going to be a similar factor for the epsilon 2 pi of k2 dot pi. Okay, so this is easy, just multiplying the same factors we've seen before. And now we have to do slightly more work in this case, here. And the reason is that the momentum of the first particle is actually modifying the contribution from the soft theorem. So let me do it here. So this is going to be the II terms. Okay, so once again, let me say that there's some momentum here. The momentum is going to be pi, and then k1 and k2. So what we're going to have is that the first factor is going to create EI, the charge of the particle, epsilon I dot pi, and then k1 dot p. But the second factor, so the momentum of this leg, this edge in here, is p1 plus k1, but the one of this one is p1 plus k1 plus k2. Right? So, oh. Ah, yes, yes. Thank you. So the typo was here. This is pj and pj. Thank you. And the charge, yes. Excellent. Any other questions? Okay. Thank you for paying attention. So then in this factor, we're going to have epsilon 2 pi, but now it's going to, instead of having the k2 here, I have k1 plus k2, because this is the momentum flowing from this edge, okay? Dot pi. Okay, in fact, all of this is multiplying the end particle amplitude. And this. You're asking about this factor in here? So this is after using the onshore conditions. This is the cancellations that we've seen at the very beginning of this lecture. And basically it tells me it's whatever the momentum that is being injected, which in this case is the sum of the two times the old one, leading order. Okay, so this was the contribution from the first diagram in here. There's also going to be a contribution from the twisted diagram. The contribution from the twisted diagram is going to be very simple because I'm simply going to change K1 with K2. Right? Okay, so this is interesting because it means this factor here stays the same, and what changes is this factor and the epsilons. Yes.
I mean, you have both of them, so it's also symmetric.
Yes, yes. The epsilons also change. Yes. As you're saying, it's not going to matter, but they change. Yes. Okay. So let's do this little exercise. So let's see. Okay. So let me copy a bunch of factors. So if EI epsilon1 PI. Okay. This is the interesting part because here I'm going to basically the only thing that is going to get affected is this term in here. Okay, so fk1 the pi plus I epsilon, and then plus the symmetric term k2 plus p dot pi plus I epsilon. And then the rest is, as before, is simply this thing copied. So let me not write it down. Okay. But now, actually, let me write it down because to see the cancellation. Okay. So now it's very cool because what I can do is I can combine these two factors into a common denominator. You can see what's going to happen is that in the numerator, I'm going to have K1 plus K2 dot pi plus I epsilon. So it's going to cancel this one. And then the only thing that is going to survive are the two denominators multiplying each other. Okay, so what this is going to give me is two factors. Okay, and hopefully no typos. Okay, and what is this? Well, we've analyzed the II terms, and we see that they take the form of the same term after this magic cancellation between the two contributions. So they actually fill the diagonals in this expression here, right? So this means that if I sum over every single term, I can essentially copy this, but erase the restriction to off-diagonal terms. So just include everyone. Okay, so this is a very interesting observation, and in fact, it turns out to generalize. I should say, if you can actually remove this I not equal to j, it means that there's factors that only depend on I, factors that only depend on j, and sum over ij. So it's in fact a product of two terms, right? So in general, what you're going to find out, if you repeat the same exercise in the case of the S soft photons, you're going to find that you have a product of S particles. And then for each of them, the soft theorem is going to look like this. Once again, to leading order. Okay, and now I'm realizing I'm out of time. Is that right? Yes, so the question was about the specific limit that I take. You're absolutely right. The answer actually tends to depend on the specific order of limits. So what I'm taking here is I'm taking all the soft particles to be soft simultaneously at the same rate. There would be subtleties if I try to first take one of them to be soft and then the second one to be soft. So if there's a different separation of scales. Okay, I actually think this might be a good stopping point. In the next lecture, we're going to analyze the counterpart of all of this for virtual radiation, which is going to basically utilize a lot of the same steps, but the story is going to become more and more interesting. Okay, so thank you.
So are there any urgent questions? Or otherwise, we can have a coffee break and come back at 11:30. Okay.
Yes.
I don't know if we're going to discuss this, but can this thing be used if you assume the difference and maybe like studying with that, but if you imagine having more than one type of graviton, like does this thing rule out this kind of